In this section, we discuss the issues that arise when photovoltaic systems are integrated into the electricity grid in large quantity. We have discussed how the grid voltage can be affected by distributed generation, like PV. But there are other issues as well. In this video, we will focus on the power and frequency issues. The learning objectives for this video are to understand how the power output fluctuations disrupt the electricity grid. You will learn about the power factor corrections, and we will discuss frequency and harmonic issues in the power supply. Fluctuations in the power output are an inherent problem for distributed generation. This is a problem especially for the utility manager, who must guarantee power to be transmitted to the different loads. In traditional power systems, the power is injected by constantly making power plants into the grid, making management of the power generation according to the system load relatively simple. Now, with widespread diffusion of distributed generation systems, grid management has become more complex. In fact, PV systems show a peak when the irradiance is at maximum over the panels. This usually occurs around noon, while during the night no electricity is provided. Weather conditions such as cloud cover can also cause power fluctuations. These short-term fluctuations can cause problems with the quality of the power that the load receives. In order to minimize the impact of power fluctuations, some different strategies can be adopted. For example, by means of geographical dispersal, it is possible to have simultaneously 2 or more PV farms that receive different solar irradiance or that are subject to slightly different weather conditions that can affect power production. Moreover, for longer-term fluctuations, backup generation is required in order to maintain power supply. Another good way of managing intermittent power inputs into the grid is to forecast the probable PV production in selected areas. Meteorological data are used to predict the PV behavior. Grid operators make intensive use of forecast algorithms to control power flows and guarantee a constant feed to the loads. Nevertheless, these forecasts may predict less power than a PV system is actually able to produce. In this case, traditional power plants are shut off to avoid a surplus of energy in the system that could cause faults or could end in wasted power. Alternatively, this excess energy can be stored if storage is integrated into the grid. On the other hand, the forecast might also be higher than the actual PV production. In this case, backup power generation is needed to cover the energy demand. It is clear that even though forecast algorithms could be very accurate, these are nonetheless affected by unexpected weather conditions or problems in distributed generators. Another way of coping with power fluctuations is the installation of storage facilities. In this case, when the power output of the PV system is higher than the demand, the excess can be stored and then reused when necessary. Battery systems are characterized by very fast response time. With the dropping price of lithium-ion technology, this solution is becoming more and more tenable. Fluctuations in the power output can cause transients in power supply, which will affect the quality of the power. These transients decrease the power factor, which is defined as the ratio between the real power in watts and the apparent power in volt-amperes. The apparent power is the sum of the active and reactive power. But what do I mean by active and reactive power? Well, transmission lines have a certain inductance and capacitance. Due to this unideal impedance, some of the AC power traveling through them is recycled through the lines and never reaches the load. This is known as reactive power. The beer mug analogy is a very common and intuitive way to explain the effects of power factor on the electrical grid. Let's suppose the beer is the real power in watts, while the froth on top of it represents the reactive power in volt-amperes. As seen before, the sum is called apparent power in volt-amps. Although a customer pays only for the beer, he will receive also some undesired froth that will occupy the space in the mug, thus decreasing the quantity of the beer received. So what does this have to do with PV? Well, there are control circuits in place to reduce the amount of reactive power in transmission lines. However, these circuits are specifically tuned to a predictable power source. With PV, the power output is not predictable. This means that the amount of reactive power may be greater than desired, reducing the power factor of a grid. This is something grid providers have to become more and more aware of as distributed generation becomes more substantial. Another aspect that can be affected by PV is the grid frequency. The grid works at a constant frequency of 50 Hz in a large part of the world and 60 Hz in the Americas and parts of Asia. In order to avoid problems with the functioning of the loads, frequency must be uniform throughout an interconnected grid. Control loop mechanisms built into the power generating sources are able to maintain a balance between connected load and generation with a small deviation in frequency. Also, disruptions in the balance between the supply and the demand lead to frequency fluctuations. In particular, the frequency of a system falls when demand exceeds supply, and in the other way around, frequency rises when the supply exceeds the demand. Again, with less controlled distributed generation like PV, this becomes increasingly difficult to control and monitor. With increased PV penetration, there is an increased chance of power fluctuations, which can result in frequency fluctuations. These frequency fluctuations can be very damaging to the loads connected to the grid. Harmonic content must also be taken into account when analyzing the high penetration of PV power into the grid. Harmonics are spectra with integer frequencies, multiples of the fundamental power frequency. Let's consider the voltage output waveforms of a PV inverter working in the square wave mode. The red square wave can be approximated by the sum of an arbitrary number of sinusoidal waves by mean of the Fourier series. The first harmonic, or fundamental, is a pure sinusoid, and it is the one carrying the active power. Nevertheless, also superior harmonics are present and injected into the system, contributing to the harmonic distortion of the signal. All electrical appliances and generators produce harmonics and therefore are regulated under close standards. In large volumes, these harmonics can add up, causing interferences, malfunctioning of devices, and even fires. In order to reduce the harmonic content, filters can be used. Filters use capacitors and inductors, either in parallel or series, to cancel out the lower or higher harmonics from the output power. Apart from passive filter circuits, some more expensive active harmonic filters can be used. The inverter of a PV system produces a square wave signal. This signal can be divided into the fundamental wave and the harmonic wave. An active filter injects into the grid a harmonic compensation wave that evens out the distortion. This way, a filtered wave can be delivered to the grid, and without these filters, the harmonics provided by the inverting DC signal can be very detrimental to the overall grid health. We have seen these two lectures how adding a large amount of PV generated power into the system requires a lot of effort, and progress has to be made into this direction. You have learned that distributed generation such as PV can cause issues with voltage, power, power factors, grid frequency, and harmonics. These problems will become greater with increased PV penetration, and smart grids that can control for these inconsistencies need to be developed. It is important that as a PV systems engineer, you understand the bigger picture when it comes to integrating PV into the grid.